Hello everyone, welcome back to the Saga Tech Gate. In this video, we'll explore procedure blocks used in a Verilog. Especially we have two procedure blocks, always and initial. These procedure blocks are used to describe the sequential logic as well as the combinational logic in Verilog. Let's get started. Always and initial. So Verilog behavioral model contains a procedure block. As we see in the last video, if we want to describe a model or a digital system, in behavioral modeling, we'll use the procedure block like always. So what is mean a procedure block? A region of code containing a sequential statement. They execute in the order they are written. So the procedure block contains some statements. Those are the sequential statements. They will execute in the order they are written. So we have two type of procedure blocks in Verilog. One is always, another one is initial. So always block execute forever, execute whenever sensitivity list changes. Along with always block will provide some sensitivity list, nothing but it contains some list of signals. Whenever these signals are changed, then always block will execute. So we have another initial block. So execute once at the beginning of the simulation time. Nothing but at a zero simulation time, it will start execution. Especially this initial block is used only for test bench purpose, whereas this always used for design purpose. So a model can contain any number of procedural blocks, all of which execute concurrently. The model may contain n number of procedural blocks, all which execute concurrently. Each always and initial statement represent a separate activity flow in the Verilog. Each activity flow starts at zero simulation time. So each always and initial block in the Verilog code represents some activity. Okay, it contains some sequential of statement. By executing those, it will provide some activity. So each and every always and initial will start at zero simulation time only. So the activity is stopped only by a power of $finish or maybe a pause, maybe an interrupt by using $stop. So this $stop and $finish are the system tasks. Okay, this is used to stop the simulation. This is to pass the simulation. Okay, so the always and initial cannot be nested. So we cannot write one always statement in inside of another always. We cannot write initial in inside of another initial block. We cannot nested these always and initial. So now by using a $finish, we'll stop the complete simulation. We close everything. Whereas by using the $stop, we'll just pause that simulation. We'll hand over to the simulator. Okay, so we'll discuss these two in later videos. So first, always block. So the always construct repeat continuously throughout the duration of simulation. So it repeats continuously throughout the duration of simulation. It executes continuously based on the sensitivity list. So this construct is used to model a block of activity that is repeated continuously in a digital circuit. For example, if any module, okay, any logic want to execute continuously, then we'll use this always block. So this is the syntax for always blocks. Always at the rate sensitivity list. So now begin and end. These are the statements written inside the always block. That may be a procedural block, okay, procedural statement. That may be blocking or non-blocking. So these are the sequential statements. So now always at the rate sensitivity list. Here we will provide the list of signals. Whenever these signals are changed, then this always block will execute. So we'll write a begin and end statement. We write this sequential statement in between begin and end. Remember, in Verilog, if you write any statements between begin and end, those are the sequential statement. This is a thumb rule. So now this is a simple syntax for always. Now what is the example? If you see the simple example, clock generator. We want to generate a clock continuously. Clear? So always #5 clock equal to negation clock. So now what is this here? This is the #5, this is a time delay we are providing. So after each and every 5 units of delay, then clock will be inverted. Clock equal to negation of a clock. Now this continuously will generate a clock by using this always block. So sensitivity list, a list of signals, events that trigger the execution of the always blocks. So these are the list of signals are used to trigger this always block. Whenever these signals are changed, Okay, then it will trigger and it will execute. So assigning LHS inside always block must be reg type. So what are the variables or signals used as LHS? Okay, in this always initial, those should be reg type only. So the always can be used to model both combinational as well as the sequential logic. If we see combinational logic, execution triggered based on the inputs to the logic, that may be nets or variable on the right hand side of the assignment statements. So here the execution triggered based on the some inputs, that may be a net type or maybe a reg type. Okay, right hand side of the assignment statement inside the always block. Whereas in the sequential, execution triggered based on the clock event, sometimes clock as well as the reset event also. Whereas in the sensitivity list, for a sequential logic, we use a clock as well as the reset. Whereas in a combinational logic, if you want to design a combinational logic by using this always, the sensitivity list should be any variable either net or reg type, the two on the right hand side of the assignment statement. Whereas in sequential, we'll use clock or reset, sometimes clock and reset. So let's see some simple example how to model this combinational circuit by using this always. So now see this 2:1 mux using behavioral modeling. Simple. I'll use always here module name, y is the output, I naught as I1 as the input, and S is the selection line. Input wire I naught I1 S. Then output is a reg type, that is a Y. Because it is LHS in this always block, so it should be a reg type. Always at the rate. Whenever the input changes, I naught or I1 or maybe signal, that selection signal changes, whenever this I naught or I1 or S changes, immediately it will trigger, it will execute this always block. So begin and end. So if S is equal to 1, then Y is equal to I1. Else Y is equal to I naught. This is a simple 2:1 mux in a behavioral modeling. By using this always, we can write here. So this always will execute continuously based on this sensitivity list. If any signal changed in this sensitivity list, immediately this always block will trigger and will execute. Same way, if you see in the sequential, how do we use this always block to model a sequential circuit? So model D flip-flop has a two inputs, okay, clock and reset, another actual input D, and output is a Q. So input, the clock, reset and D, the output is and reg Q. Clear? Always at the rate passage clock. So now what is the meaning here? We'll use a passage. Okay. So whenever the clock changes from 0 to 1, passage means 0 to 1, negate means 1 to 0. Whenever the clock changes from 0 to 1, then this always block will execute. So if the clock changes from 0 to 1 at each and every passage of the clock, then if reset equal to 1, then Q equal to 0. Else K equal to D. This is a simple D flip-flop using a behavioral modeling style. So now here you may find this is equivalent, these are less than or equal to. So here this is a blocking statement, these are the non-blocking statements. We'll discuss about these blocking and non-blocking statement in further videos in detail. So now if reset is 1, then Q equal to 0, else Q equal to D. This is a simple D flip-flop using a behavioral modeling style. Clear? I hope you understand. So we use this always to describe the behavior of combinational as well as the sequential logic. Now see this example. So model mux 2:1 input A comma B wire, input wire selection, output reg out. So inputs are A comma B selection and wire type. That out should be a reg type only because it is LHS in this always block. So now always at the rate A or B or selection line. If A changes, B changes, selection changes, then this always will execute. If selection line equal to 1, then out equal to B. But what about else part? If selection line is 1, then out equal to B. If selection line is 0, then we didn't write any logic. So we cannot write like this. Clear? So now missing else. Okay. So if selection line is selection line is 1, then out equal to B. What about if selection line is 0? Clear? We should write that case also. Missing else here. Yes or no? So else. If you write correctly, if selection line equal to 1, the out equal to B. Else out equal to A. So missing else. out is not assigned when selection line is 0. If selection line is 0, okay, so if selection line changes, then it will trigger this always block, but there is no logic for selection line equal to 0 because it is missing else part in this. Yes or no? So out is not assigned when selection equal to 0. So this is inferred a lodge. Why this inferred a lodge? When selection equal to 0, the if condition is false. Since there is no else, the value of output is not updated. Clear? So Verilog assume that output, okay, must hold its previous value. That out must hold its previous value. So this behavior maps to a latch. So now when selection equal to 0, so it is if condition is false, nothing but this a condition fails, then there is no else part, so the value out is not updated. So in that case, Verilog assume that the out must hold its previous value. So in that scenario, the out must hold the previous value as it is. So this behavior maps to a latch. So it infer a latch. Now what is the correct code? So always @ You can write A or B or selection line or always @ Both are valid. So this modern way to write. So it take automatically all sensitivity list. Clear? Always @ begin if selection equal to 1, out equal to B or out equal to A. This is the correct way of writing logic for 2:1 marks in a behavioral modeling. So in Verilog, if output might not be assigned to some inputs cases, right? So the synthesis tool inferred a lodge to remember the lost value. So if output may not be assigned to some input cases, then synthesis tool infer a lodge. So it should remember what is the previous value. Okay. So the better cover all conditions in if or case Z statement to prevent lodge inference. Okay. So better use all condition. It cover all condition in case of if, else, case X, case Z, okay, statement to prevent a lodge inference. I hope you understand. If you miss else part, then it inferred a lodge. So what is this? It is a combinational circuit. Yes sir. No. Our intention is to design a combinational circuit. 2:1 marks is a combinational circuit. But if we miss the else part, then it inferred a lodge, means it is a sequential circuit. So make sure that, okay, better it cover all condition. If you write if or case, okay, so in that case, you should mention all the possible conditions to prevent the lodge inference. I hope you understand. So now next coming to the initial block. An initial block start at time 0, execute only once during a simulation. An initial block is not synthesizable. This initial block especially used only for test bench purpose. Clear? So if there are multiple initial blocks, each block starts to execute concurrently at time 0. If it contains more than one initial block, all will execute concurrently. That too all will start at time 0 simulation. So execution of initial block finish all the statement within the blocks are executed. So when should I say that initial block is completed? All the statement written in the initial block all executed. Then only, okay, we can say the initial block finishes. Okay, completed that initial block. So the initial blocks are typically used for initialization purpose and monitoring and other purpose that must be executed only once during the entire simulation run. So when we use this initial block, especially used for initialization purpose and monitoring some variables and other purposes also, okay, other processes that must be executed only once during the simulation run. So I want to execute this logic only one time in my whole simulation, then I'll use the initial block. Remember, the initial construct not synthesizable. We never use this initial construct in the design. Especially this initial block is used for only in test bench purpose. So this is the simple syntax: initial, begin and end. All the statement written are in the sequential statements. Clear? Same like always, but there is no sensitivity list here because it will execute only once, that to 0 simulation time. Clear? The statement written in these initial blocks are the sequential statement. That may be a blocking or non-blocking statement. So even though you know that the statement written in the begin and all are the sequential statement, they will execute in the order they are written actually. So now see this example. I'll discuss a simple example that you to get an idea. So here I'll generate one model stimulus having the like simple. I'll take reg x comma y a comma b. Just I'll declare those as the reg type. So how many initial blocks? Initial here m equal 1 tick b 0 single assignment. Initial begin and end. Here are two multiple statements are there. Here also another two statements are there. Clear? So initial here another initial block is there. Yash $50 finish. I want to finish this simulation. Right? So how many initial blocks are there here? 1, 2, 3 and 4. 4 initial blocks are there. So if the model contain n number of initial block, more than one initial block, all will execute concurrently and it will start at 0 simulation time. So each initial statement represent a separate activity flow in Verilog. Each activity flow start at simulation time 0. It will represent some activity. It will represent this initial block represent another activity. This initial block represent another activity. All will execute concurrently. The two all will start at 0 simulation time. We'll see. So now the activity is stopped only by power of $finish. It terminates the complete simulation. Whereas by using a $stop may it pass the simulation sometimes. So now see, we try to understand. First, how many are there? 4 initial blocks there. Which one execute? All will start execute at 0 simulation time. But now see, it will execute first because there is no delay. So m is equal 1 tick b 0. After that, then which initial block? This initial block will execute because here delay is the 5. After 5 units of delay, then a equal to 1 tick b 1. Then it wait, okay. So what is the next? So 25 simulation, like yash 25, nothing but yash 25, nothing but. So we are providing a delay 25 time minutes. So now it should wait next 25 time minutes delay, right? Instead of that, if you see in the third initial block, here this x equal to 0, when it should wait only at 10 time minutes of delay. So here 5 time minutes of delay, a will update as a 1. After 10 time minutes of delay, right now here is a timestamp 10, then x is equal to 0. Then it will wait, okay, 25 time minutes. Then at 30 timestamp, okay, at 30 timestamp, then b equal to 0. Whereas here 10 plus 25, yes or no? Here at 35 timestamp, y equal to 1 tick b1. So simply m equal to 0 and 0 simulation time. At 5, a equal to 1. At 10, x is equal to 0. And at 30, 5 plus 25. At 30, b equal to 0. And at 35, y equal to 1. And at the timestamp 50, then we'll terminate the simulation. If you see the output here, at time 0, m is equal to 0. At 5, a is equal to 1. So now at time 10, then x is equal to 0. We'll execute this. At next, at 30, we'll execute b is equal to 0. At 35, y is equal to 1. Then at 50, then we'll finish this. Because each and every initial represents separate activity. All will execute concurrently and they start at 0 simulation time. So now I hope you understand, right? By this example, all will execute concurrently. But we are providing intentionally these delays, okay, to understand the behavior, right? Now see this another example. So here module TB and reg clock. So what is that here? Clock generation. So initial clock equal to 0, right? So why the clock is equal to 0? We know that, okay. So right, initially we declare the reg. What is the default value of reg? We know that, okay. So better you initialize with the clock equal to 0. Initial clock equal to 0. It will execute only one time, that to 0 simulation time. No clock equal to 0. Then always hash 5 clock equal to negation clock. Clear? What is the meaning? Every 5 minutes of delay, clock will be changed, okay, the complement of that clock. So here now see, this is the clock. We see what is the clock here. After each and every 5 minutes of time, 0 become 1. After 5 units of delay, it becomes 0, okay. After 5 minutes of time delay, it become 1, like that. We'll get a clock. Continuously clock will generate it, okay. So why we need this clock? So if you design a simple digital system, so we need to test that one. Then the simulation, okay, in the test bench, you need to generate the clock. We need to provide the clock to that design. So we need to generate clock in our test bench. So like simply we can write initial clock equal to 0, always hash 5 clock equal to negation clock. Like that we can generate the clock. What is the time period here? So 5 plus 5. Time period is the 10. Now initial begin. So here one procedural block is another always and another initial. Okay, initial begin, because multiple statement we've written, so we'll use a begin and end. If only one statement, no need to write a begin and end. So initial, begin and end. So I'll use a simple display statement. Starting the simulation time equal to ampersand 0t $time. Just $time, you know that it returns the current simulation time. Already we discussed earlier. So $time returns the current simulation time. You know that what is it returns? All initial and always will start execution 0 time. So immediately it returns 0 simulation time. Okay, it returns 0. So it wait 50 time minutes. Then after that it finish. Okay. So here another always block is there. So whenever the clock is changed from 0 to 1, passage clock. Whenever is clock changed from 0 to 1, then this always block will execute and it will display this. Okay, $time. Okay, we have a 2 display statement. It will execute only one time. This display is execute whenever we'll get a passage clock. But this display execute only once, because initial construct execute only one time at 0 simulation time. Now see, this is a clock. We'll get passage clock means 0 to 1. Every passage of the clock, then this display statement will execute. Now see, this is the output for a given program. So what is that first? So we have two initial blocks and 2 always blocks. So initial block will execute only once. So initially clock equal to 0. The initial begin. So now this display will execute starting the simulation time at 0t. Now starting the simulation time, so it returns $time returns the 0. Okay, 0, because it execute only 0 simulation time, because it should wait till 5 time minutes delay. This always block. This always block trigger only whenever we will get a passage of clock. So these 2 initial blocks will execute first compared to this always. This always wait for hash 5 and this always wait for passage clock. Whenever after 5 time minutes of delay, clock becomes 0 to 1, then immediately this display will execute. Okay, always trigger at time equal to 5, because $time returns 5. Yes or no? So now after 5 time minutes of delay, what happened? Then this clock equal to 0. Clear? Then after 5 time minutes of delay, clock become 1. So at the time of 15, okay, at the time of 15, we'll get this clock pulse. It's yes or no? So it is at 5, then at 10 we'll get a 0, and at 15 1. So 0 to 1. Then this display will execute. Similarly, here at 25 we'll get another passage clock. This display will execute. At 35 also will another passage clock will execute till 45 will execute. After 50, then we'll execute this $finish. I hope you understand. This always block will execute only whenever we'll get the passage of the clock. Okay. So at 5, 15, 25, 35 and 45. Okay. It will execute after each and every 5 time minutes of delay. Clock will change. Okay. After 5 time minutes of delay. Clear? I hope by this example you understand. Okay. How we are generating clock. Understood what is mean passage clock. So this display statement will execute this always block trigger only whenever we'll get a passage of the clock. Passage of the clock means whenever a clock change from 0 to 1. So at time, which time step this clock becomes 0 to 1, that time step only it will execute. Now see this another example here. So module TB reg clock. This is a simple clock generation. Initial clock equal to 0. Always clock equal to negation clock. Simply. Clear? Complement clock we simply can say. So here I didn't specify any delay. In the previous example, I'll specify the delay here. But I didn't specify the delay here. What is the meaning here? So always an initial will execute continuously. If I write there is no sensitivity list, nothing but it will execute continuously. So within 0 simulation time. Okay. It started 0 simulation time. There is no time to update this one. Anyway, forget about initial and always. Same statement. Just I'll change this. Okay. Just I remove this time delay here in this example. So what is the output we'll expect? So warning. Potential always loop found. This is the potential always loop found at test bench 6. If you execute this code, we'll get a warning. Okay. At testbench.sv. At line number 6, we found a potential always loop. This always block has no event control or delay statement. There is no event control at the rate or any sensitivity list, or there is no delay. It might causes an infinite loop in simulation. This is a warning I got in VCS. Clear? So execution interrupted or reached maximum runtime. This is the error we got. After executing this program, we'll get this error because it is an infinite loop. Within 0 time, the clock will update it. Clear? So there is no time to trigger other blocks, procedural blocks in this code. Once it enter into this always, continuously it will execute. There is no time to execute other procedural blocks in this code. Clear? Right. So now infinite assignment with no time delay leading to simulation error or infinite loops. This means hang simulators. This is the error we get actually. Either maybe simulation error or maybe infinite loop hang the simulator. So now, so make sure that you should provide some event control or delay in case of this always here. Or else in this statement especially particularly it will execute continuously. Within 0 time it will execute. Clear? There is no chance to execute all remaining procedural blocks. So sometimes the simulation may be hang. It was go into the infinite loop. So in this video, we discuss procedural blocks like always and initial with some suitable example. These are very important. Okay, especially these always blocks are used to define a logic, maybe a combinational or sequential logic. So whenever that logic wants, like we want to continuously execute that logic, then we'll use this always. So initially is used in test bench, okay, to generate different stimulus and also clear to monitoring the various signals in that our design or for various processes. And this initial construct is not synthesizable. We never use in the design modules. So I hope you understand these procedural blocks used in a Verilog. Thank you very much.